So students, we are studying universal law of gravitation, and we have suppose sun over here, and then we have earth, and earth is suppose moving around the sun, and then we have moon, which is moving around. So this is my moon. And this is your earth. So what we are studying here is that the moon revolving in an orbit of radius rm. So this is your earth, and this is suppose orbit of the moon. So there you have moon over here. Now orbital radius means center of earth, center of moon. Join center of earth to center of moon. This is the moon's orbital radius. So the moon in the orbit was subject to the centripetal acceleration. So the centripetal acceleration, center seeking acceleration, this is AC due to Earth's gravity. So what's the value of AC? We know the value of AC. So here we are writing centripetal acceleration of the moon. Who is accelerating? Moon is accelerating. So centripetal acceleration is C means centripetal here, and here M is moon. So centripetal acceleration of moon is equals to V square by Rm. This Rm. So so here centripetal acceleration we are calling it as Am. Now we have two ways. Further, we know that V is equals to omega r, and also we know that V is equals to 2 pi Rm, means the circumferences divided by time period of the revolution. So two ways to move further. So put the value of V here, we get centripetal acceleration of the moon is equals to, this R is your Rm, of course. So this Am is equals to omega square Rm square upon Rm. So this one Rm will cancel out and you get omega square R. That's the centripetal acceleration. Okay, we have the formula. We did it in I think chapter number 4, omega square R, centripetal acceleration. And from here we get putting this value over here, so squaring it, 4 pi square Rm square divided by this Rm, and so this V square means this square and T square. So this is V square and divided by Rm. So divided by Rm. So here also one Rm cancels out, and we get Am is equals to this 4 pi square Rm. So this is what is written in as equation 8.3. Okay, so V is the speed of the moon related with the time period, and V, this time period, this formula is also given. That's V. So the time period is about 27.3 days. So how much is the time period? So what is Rm? Rm is equals to 3.84 into 10 to the power 8 meters, and T is equals to 27.3 days. Okay, so change it into seconds. Okay, multiply by 24 and then multiply by 3600. Okay, so you'll get it in second. 27.3 into 24 into 3600 seconds. Now putting these values over here, a value of Rm, T, we know pi is equal to 3.14 square of it. So we get students, Am is equals to 2.7 into 10 raised to minus 3 meter per second square. So that's the acceleration due to gravity. So this is 3.84 into 10 raised to power 8 m radius of orbital radius of the moon. If we substitute these numbers in equation 8.3, we get a value of Am that is much smaller than the value of acceleration due to gravity. See, this is much smaller than 9.8 meter per second square. That is your acceleration due to gravity on the surface of the earth. So this is the surface of earth, and arising due to gravitational attraction. Is this okay? Now further, so what this shows? This shows that force due to Earth's gravity, it decreases with distance. So here was the Earth and the moon was over here. So on the surface, its value is 9.8 meter per second square, acceleration due to gravity. Whereas the acceleration, the centripetal acceleration of the moon is 2.7 into 10 raised to power minus 3. So it means this gravitational force decreases with the distance. So we can assume that this gravitational force due to the earth, it decreases in proportion to the inverse of the square from the center of the earth. So this distance r is, we know that we take h and g, sorry, r and h. So when we take r is any point this distance, and h is, so when we take r, g varies. Okay, and when we take h, which is this height h, which is near to the surface of the earth, so here we take g constant. Okay, so here we take g as a constant in this case, and here we take when we take r, it means g is varying. This very near to the surface of earth, this height h, from the surface we take g as constant. So here this fg is proportional to square of the inverse square of the distance from the center of the earth. So we have, so if f is proportional to this, so f is equals to ma, so that's mass of the moon into acceleration of the moon, that is am. We just calculated. So it means that f is equals to m into am. So m is constant, so it means am is directly proportional to 1 upon rm. So if I'm using here am, then it will be rm. So it means that am is in proportion to the inverse square of the moon's orbit, moon's orbital radius, right? Now this acceleration due to gravity is for the surface of earth, So instead of Rm, what we will have here? Here this is radius of Earth. So on the surface of Earth. So G on the surface of Earth is proportional to 1 upon. Here we will take radius of Earth square. Okay. So of course we will have proportionality constant, and that will cancel out, and that the proportionality constant here is equals to, or we will be writing am is equals to k, and here g is equals to k, and this k will cancel out, and what will be the value of g upon dividing these two equations? So this will be, suppose, equation 1, this is equation 2. So equation 2 divided by equation 1 gives g upon am equals to, so g upon am, that will be k upon re square divided by k upon rm square, and that will be equals to, so k cancels out, and this rm, so this is 1 upon rm, so rm upon 1 into 1 upon re square, that is this. So this is what you get here, and this value is approximately 3600. Okay, and this value means g upon am is an agreement with the value of g as 9.8, and am that we calculated above, that is 2.7. so that is in agreement with this. So it means that our assumption is correct. Okay, so these observations led Newton to propose the following law of gravitation. So here is the law of gravitation, students. This is the law that you need to write. Every body in the universe, so that's the Newton's law of gravitation. Every body in the universe attracts every other body with a force which is directly proportional to, so all the bodies in this universe, they attract every other body with the force which is directly proportional to the product of their masses. So if we have two bodies, m1 and m2, directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So if the distance between them is r, so, and as a whole we get this gravitational force is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. And we can further write this Fg is equals to constant of proportionality is g here, g m1 m2 by r square. So that's the magnitude of this force, which is equation 8.5. Now how to express it in vector form? So look here, students, these are the two masses, m1 and m2. Okay, now this is my origin, so this is the position vector r1, this is the position vector of m2 r2, so we are reaching 2, and here also I am reaching 2, but from where? Here I am reaching from origin, right? So I need not to write the origin, it's origin. Okay, but here I am reaching from 1, I am starting from 1. So relative position of mass 1 with relative position of 2 with respect to 1. So this is the position, that the first number that I am writing as subscript. So that's R21, and R21 you know that is equals to R2 minus R1. So the point here is that this R21, right? So students, now I am writing it for force. So see, force on 2 due to 1. Okay, what is the force on 2? So where this force is acting, students, where this force is acting? What is the direction of force on m? Force is the m1 m2 is attracted towards m, yes, m2 is attracted to, so that's the direction of force, that's the direction of F21. Is this okay? What is the magnitude? G, m1, m2. So what's the distance between them? So this what is the magnitude of this R21? So this is the magnitude of this R21, right? This distance is R21. So you can write here R21. Okay, square of it. So that's the distance between them. Fine. What is the direction? See, this is the direction of F21. What is the direction of R21? R21 is in this side. Yes. So do the R21 and F21 are in same direction? Yes or no? R21 this direction, F21 this direction. So the directions are opposite. That is why we need to write here negative sign. Okay. And if you are writing R21 is equals to R, then we can write it in the same way, m21 upon and divided by R21. You can write R square, and here this is, students, this that's the mistake. Okay, what's the mistake here? See, any vector is equals to its magnitude and then its direction. Direction is always given by unit vector. Okay, so that's the unit vector. So that I can write r cap. If I want to write it as in the vector form, yes, I can write it in vector form also. F21 is equals to, so that's minus R21, right? Minus here or here, that's the same thing. Okay, so writing the minus over here, so this minus will come here, that's the same thing. Now writing it in the form, in the vector form, suppose here you want to write vector. Okay, m1 m2 upon R21 square. So what's this unit vector? See, we have a vector that's equals to its magnitude, and then like here, this is the vector, this is the magnitude, and then multiplied it with the unit vector in that direction. So now unit vector in that direction. So that's how we write a vector. So what is unit vector? So unit vector is equals to vector divided by its magnitude. So magnitude will come here. So I can write this as means. So in our book, even F21 is written as F. That's all right. There is no problem with it. Okay. So there is no problem if you are writing only R. Okay. Now what's the direction here? This direction is, you can write the value of unit vector as minus. Minus is there, so keep the minus here. You can put the minus over here also. This minus will go here. That's the same thing. And students, this unit vector is equals to vector divided by magnitude. So this can be written as F is equals to minus G m1 m2 upon R cube. So this will become R cube into R. So students, these are the different ways. In your books you will find this also. In 12th class also we will have same discussion. Variables will be different, but the concept will remain the same. This way also, and this way also. So these are the prominently, this is this, and means writing it in unit cap form. So these two are, that's the same thing, and this is the second way. So don't get confused that here R square and here R cube. Here it is R cube because I have R vector. So put the value of R vector, means magnitude into unit vector. So magnitude will cancel, and again you get R square. So this is inverse square law. So inverse square law, and here it can be written in this way also. So I hope this concept is clear to you, students. So gravitational force is attractive, right? And the force F is acting along a minus r vector, means the force and this vector, they are in opposite direction. So that's r21, and m2 is the force on m2 is in this direction. So m1 is pulling m2 towards itself. So direction of r21 and f21 are in opposite direction, so that is why we have negative sign over here. The force on point mass m1 due to m2 is of course minus f by Newton's third law. So what will be the force? So this was the force on second due to first, and what will be the force on first due to second, students? Yes, force on first due to second. If you are assuming it as r and this direction as unit vector, so what will the force on m1? So force on m1 is on this side, which is in the direction of r, right? So that is given by g m1 m2 upon r square into unit vector. So that's the force on m2, force on m1. So that's the force on m1. This was a force on m2. So you can see here that here force on second due to first was, but student, if you are writing here this form, so here you are not supposed to write 2 1. So if you are writing 2 1 here also you will be writing 2 1. So if I am writing 1 2 here, so and I am writing it in terms of 2 1, so that's the, so here 1 2, but here 2 1, they are in same direction. Okay, but if I, students, hope you are understanding this. Yes. So the force on mass 1 is this. So by Newton's third law, the gravitational force F12 on the body due to 2 is F21 on body 2 due to 1 are related as, so of course this is this direction, so they are in same direction, here they are in opposite direction. So F12, so put the value of F12 here, so that's negative. So F12 is equals to minus of F21. So Newton's third law, forces are equal and opposite. So before we apply this equation 8.5 to objects under consideration, we have to be careful, since the law refers to the point masses, whereas we deal with the extended objects with a finite size. If we have a collection of mass points, the force on any of them is the vector sum of the gravitational force exerted by the other. So if we have these masses as so you can see that here we have these are the masses. So we have 4 masses over here. So what's the force on mass 1? That is force on m1 is equals to force on 1 due to 2 plus force on 1 due to 3 plus force on 1 due to m4, right? And here we are using superposition principle. So what is the superposition principle? The force between 1 and 2 is unaffected by the presence of other masses or by the presence of other forces. This is unaffected. This is also unaffected. This is also unaffected. So the forces between two particles is unaffected due to the presence of other masses. That's superposition principle. And if we want to add the force on m1, so that will be equals to force on 1 due to 2, force on 1 due to 3, force on 1 due to 4. Okay, so that's it. So force on 1 due to 2, how we are going to write it? So I have just written that F12 is equals to G M1 M2 upon. So you have two ways to write it, students. You have two ways. Okay. So magnitude. So this R square. Magnitude is same. But if you want, you have a choice. This is R cap. Okay. Now, do you want to wish it in the form of R21 or R12? So if you wish to write it in the form of R21, then it's okay. Then positive sign. But if you wish to write it in form of R12, then we will have negative sign over here. Yes, you can verify it. I have discussed it. You can verify it yourself. Because okay. So that's your choice. So here we are writing F this way we are writing. This positive way, this way. So F12 is equals to here R21, so it will be positive. Kaise? How it is so? So this is your, suppose M1. So here we have M1 is over here. Okay. This is your M1 and this is your M2. Okay. Now what's the direction of force on 1? Force on 1. This is the direction. This is the direction of force on 1 due to 2. To 2 is attracting the force. That's the direction. Okay, good. Now, what is this R21 unit vector? So reaching 2 from 1. That's also reaching 2 from 1. That's also the direction of the 2 vector. So reaching 2 from 1. So both are in the same direction, you can see. Okay. And if you take R12, so that's the direction of R12. So that is opposite direction to F12. Okay. So that is why here we have negative sign. So R21 is equals to minus, because their magnitude is same, unit vectors, but they are in opposite direction. So R21 is equals to negative of unit vector R12. Is this okay, students? This discussion is very important. Basics of physics, language of physics. Okay. I hope you have understood it. So this method we have used here means F12 written as 2-1, F13 written as 3-1, and F14 written as 4-1. So that is why they are positive. Okay. If we write it in this way, they will be negative. Shall we move forward?
Yes, sir.
So here also I told you the same thing. If it is R21, F21, R21, then it is negative. If F12 and 21, then it's positive. So same thing I have told you over here also. So students, please do the physics logically, okay? No cramming. There is no scope of cramming in physics. Everything is logical, step by step. So here we have this question. So that's the question. We have three masses, three equal masses, M. Each are fixed at the three vertices of equilateral triangle. So this is equilateral triangle ABC. What is the force acting on mass M2, which is placed at the centroid of the triangle? And what is the force if the mass at vertex A is double. So that's B part. Okay, so let's first of all let us find out, and it is given that this AB is equals to 1 meter, this also AC is 1 meter, and that's also 1 meter. That is given to you, and you have to find how much is the force acting here at G. So force acting on G, this is what we need to find. Okay, so if you assume it as 1, yes, you can assume it as mass 1. This has 2, this has 3, and this has 4. Yes, you can assume like that also. There's no problem with it. But here M1, M2, M3, M4, all of them are equal. Okay, so that's the point. Okay, now force at G, so not the small g but the capital G. See, how do we write it if we have the points? So how do we write it? Force at G due to the mass at A plus force on mass at G due to the mass at B plus force on the mass at G due to the mass at C. So that's again superposition principle, that force on the mass at G. So what is the force on mass at G? That is 2m. Now writing these values, what is FGA? So FGA is G m1 m2 upon r square. So what is the distance between this G and GA? See students, the equilateral triangle is not its sides are not 1. Okay, you have not pointed it out. See what is given. It is given that AG, BG, CG is equals to 1 meters. So AG is equals to 1 meter, BG is equals to 1 meter, and GM is also equals to 1 meter. So these distances between the masses are 1 meter. Okay. So FGA is equals to G M M1 M2, product of both the masses divided by distance. How much is the distance between this A and G? The distance is 1 meter, so 1 square. Okay, and then this is the magnitude. Now this vector, so magnitude into its direction by unit vector. So we are finding force on 2m. So where will 2m be going? So 2m will move towards m, this direction. So that's the direction of F, force on 2m, which is at G due to A. So it will be pulled towards itself by A. So that's the direction. That is y direction. So that's a vector. So unit vector J. Is it okay? So this is my direction, F, G, A. Okay, that's J cap. So J cap plus FGB. Now we are talking about these two masses. So force on G due to M. Okay, so same is the case here. Magnitude is the same. There is no problem with the magnitude. Gm into 2m divided by 1 square. So what about the direction? So see, the direction is here. So whenever the direction is not along x-axis and y-axis, we will the direction is this is the direction. So we have its component along. So if this is the direction, we have its component along x-axis and y-axis. So this is its component along x-axis and this is components along the y-axis. So which vector was it? See, this is the unit vector. The force was in this direction. Force on G due to B. That was the direction of this force, and this is the unit vector. This magnitude is of unit vector in this direction. Okay. Now this is I cap. This direction is your I cap minus I cap, because this direction is plus I cap and this direction is minus J cap. Now how much angle is this? Look here. This centroid. So all these angles are 180. 360 divided by 3. 360 divided by 3 is 180. Now this angle, and so this angle is 90 degree. How much is this angle? This angle will be 30. So it means I have this angle as 30 degree. This is 60, but this angle is 30 degree. Okay. Got it, students? So I'm not talking about so this angle is your 30 degree. Now this is 30, this is opposite side. So opposite side is equals to hypotenuse cos theta. So that's equals to minus, so that's equals to J cap cos 30. So this side is J cap cos 30 degree, right? So opposite upon hypotenuse, that's sine, not cos. Opposite side is equals to the sine cos 10. Opposite side is equals to hypotenuse sine theta. Adjacent side is equals to hypotenuse cos theta. So this is the adjacent side. This is hypotenuse cos theta. So that's cos 30 degree. And this side is opposite. So opposite to hypotenuse sine theta. So this is sine 30. So this side is minus j sine 30. This is minus I cos 30. So the direction is this direction is this plus this, right? So that's this direction. JIB, this direction is minus I cos 30 minus j sine 30. Okay. So similarly, when we talk about force on G, force on 2m at point G due to mass m at C. So that's FGC. So here also this direction I have written, and plus same magnitude, and then the direction. So what is the direction here? So similarly we can write this direction. So the only difference is that here it will be, so this is your unit vector in this direction. So what is this unit vector? This unit vector can be resolved into these components, and this is so I cos 30. So this angle is 30 degree, and this is J. So here it will be in, this J is in negative direction, so minus J sine 30. So that's the same downward, but this is on the left hand side, this is on the right hand side, and you know this left hand side x this positive minus, and this x is y, and this is so right. So that's plus I cos 30 minus j sine 30. Now adding these three, what do you get? So when you will add all three of them, Fg, so resultant you can also, that's your choice, you want to write Fg or you want to write Fr. So here G means force on the mass at point G, and you can also write it as resultant force on 2m, that is adding all these three forces, and we get what do I get from here? This is G into 2, so 2g m square j cap. Okay, 2g m square into this direction. So right, so that is equals to 2g m square into the direction that is j cap, then plus 2g m square into the direction minus I cap cos 30. So minus I cap cos 30 minus j cap, so this is theta is 30 degree here, so minus I cap cos 30 minus j cap sin 30. Okay, and plus 2g m square into what this plus I cap cos 30 degree minus j cap sin 30 degree. So you can clearly hear also students that these two are in this minus and this plus, they are equal opposite directions, so they will 2g m square, so they will cancel out, right? And what about the rest? So you can see that we have common 2g m square is the common, right? And what we are left with here, I have j cap, and what do I have here? Minus j cap into what is sin 30, that's 1 by 2, minus j sin 30 1 by 2, so that's equals to 2g m square j cap, so j cap by 2 minus j cap by 2, so that's minus j cap, and they will cancel out and the result is 0. So this force is 0 if you are writing here in terms of vector. So here also there should be vector on 0, so 0 vector, null vector. Obviously this is symmetry, so in all the three directions it is being pulled, this mass 2m, so one expect on the basis of symmetry that the resultant force ought to be 0. Now second part, what if instead of 2m I have 4m, okay, at the center? So what is the difference if I have 4m at the center? So if the mass at the vertex is doubled, so then the magnitude will be doubled. Sorry, not the mass at the center is doubled, but the mass at A is doubled. This m becomes 2m. Okay, so here the only change will be here. So here it will be, earlier it was 2g means g into 2m into m, right? We get this 2g m square, but now it's g into 2m, and the vertex at vertex A also I have mass 2m, so 2m divided by 1 square, so here I have 4gm square, so only this value will be changed. Instead of 2 I have 4 here now in second part. Rest of the things will cancel out and will remain same. So here it is 4, so here I have 2, right? And here also I have 2, because 1 2 I have taken out, so here it was 4. Okay, so now what? So now the force will not be 0 in second case when the mass 2m is there at vertex A. So now it will be 2g m square j cap. So that's the net force 2g m square j cap. Obviously, because now here the mass is m and m, they are still the same, and if it was m then it is in equilibrium, but now I have doubled this mass, so the force on this side is doubled. Okay, so that is why it is being pulled. This mass will be pulled in this direction by this much force, by gm m square. So I hope this is clear to you, students. Now we have studied the gravitational force between the point masses, but what if instead of point mass you have an extended body? Especially we are discussing here case of Holo shells. So Holo shell we have two possibilities. One is mass outside the shell, and in another case mass inside the shell. So here I have this shell, here also I have this shell, and in one case the mass is outside at this point, another case mass is inside at this point. Okay, so what if the mass is outside? What if the mass is outside? So this is the center, and it has mass m, this holospherical shell. So these are the two cases that we are going to discuss, means between the extended body and the mass m. So Holo shell, mass is outside and mass is over here. And you say, sir, what about if the mass is on the surface? On the mass of surface and the mass, then there is no distance between them, so sort of it gets stick over here. So part of this, so this m is part of this. Okay, so r is 0, infinite force part has become part of it, stick to it. Okay, so that is why two cases, outside and inside. So if it is m outside, see, all the particles of, like, see, how do we how do we calculate these kind of things in physics? What do we do? See, look, this mass m, this capital M, this holospherical shell. Now suppose I have, so this holospherical shell consists of lot of particles. So there is one particle over here, so of course there will be a particle exactly symmetric to it. So this particle will pull this mass on this side, and this particle will pull this mass on this side. So there will be these two forces. What will be the resultant of these forces? What will be the resultant? See, resolve it into components. So this is the component of force along y-axis, and this is the component of force along in the x-axis towards the center, right? So to the center, this x-axis. And now what about this, the lower one? Here, due to this, the force is in, the component will be in this direction and in this direction. So you can see that these are equal and opposite, because these are symmetric points. So these two forces, equal and opposite, they will cancel out. So we are left with only one force, that is towards the center. Yes? So similarly for all the points, like this point, their perpendicular components will cancel out, and their horizontal components, which is towards the center, they will be added up. So that is why the net force on M will be towards the center. So we can assume that in this case, that this sphere is actually behaving like whole mass is concentrated at the center, and its mass is m, and we have this point mass m. So this mass m will be attracted towards this center. So that's what is written over here. The force of attraction between a hollow spherical shell of uniform density and a point mass situated outside is just as if the entire mass of the shell is concentrated at the center of the shell. And this can be understood as I have just told you. that gravitational force caused by various regions of the shell has components along the line joining the point mass. So along the line joining the point mass, as well as in the direction perpendicular to this line joining the point mass. So this perpendicular direction. The components perpendicular to this line cancels out when summing over all the regions of the shell, leaving only the force along the line joining the point to the source. The magnitude of the force works out to be stated as above. Okay, so we can calculate the force. Now if it is inside, so again it will be symmetrical. Like I have a point over here, so it will pull it towards itself, so all this mass is being pulled by all the particles in all the direction, and if you will add up all these forces using calculus, you will find that net result, net force on M is equals to 0 here in this case. So force on M is 0 if mass is inside. Okay, so students, this is what the topic number 8.3 was. The force of attraction due to holospherical shell of uniform density on a point mass situated inside it is 0. So the force of attraction on the mass inside is 0. So what's the implications of it? So implications of it we will study here in the topic 8.5. Like you can see here, we have taken this mass M. Okay, so this is Earth's surface. Now we have divided the Earth into concentric spherical shells. Concentric spherical shells. So for these shells, this mass will be inside the shell. So mass inside the shell, the gravitational force due to these outer shells will be 0 on this mass. And these are the inside concentric holospherical shell. And so this M mass is outside these shells. So we assume that all these shells, like their mass is concentrated at the center. Okay, so and the gravitational force will be only due to this much mass of the Earth. Okay, only this much mass of the Earth, not the outside one. Is this clear? So this is this is the concept that we will use while finding the acceleration due to gravity on the surface of Earth. Right? So I hope you have understood this concept, students. So now let us do this small topic, gravitational constant also. See, we have first of all forget this, cross these two things. Okay, so we have this rod AB, and this is the wire which is hanged with, and these are the two small spheres, lead spheres, which has very high density at the 2 points of this rod. So obviously this rod will move this side, okay, little bit, and this wire will be twisted. So actually this, see this direction is shown this according to this dotted sphere. So so if you want to draw this, so this should be the direction, because rod is going to rotate in this direction. So direction also you need to correct. So students, you need to do everything logically. Okay, so that's what logic says. So it is telling you either take this dotted position or take this position. Okay, sphere means one on if one is on one side of rod, then another big sphere will be on other side of the rod. So these two are on opposite side of the rods, on two separate sides of the rod. So if you are taking the dotted, if you take the spheres over here, then they will twist. Then it will twist in this direction, this wire. Okay, but here this wire, so make this direction correct also. Now what will be the gravitational force on these small masses A and B due to these big spheres? So definitely it will be attracted towards this sphere. See, there will be very small deflection, and we have different instrument. It might be you will not be able to see the deflection theta. So this rod will be very, very small deflection that you might not be able to see it with naked eye. So we have special apparatus to measure this angle. Theta will be very, very small. Okay, and so this wire is twisted, right? So there will be restoring torque here, okay, due to this, which depends on theta. Like we have spring force that is equals to whose magnitude is equals to kx. So like I have spring over here, right? And if you stretch this this spring, so that's your displacement x. So more you are stretching, more will be the spring force. So here also, first of all, let us write the gravitational force. The length of the rod is students, that is L, and this distance is d. Okay, so length of the rod is L, and this distance between this sphere and this distance is d. From the center of both the spheres we take this distance. Okay, now let us read from here. If d is the separation between the centers of the big and its neighboring small ball, m and m their masses, the gravitational force between them will be F is equals to g. This is mass m, this is small mass m, and this distance is d. So g m upon d square. If L is the length of the bar, then what is torque? Torque is equals to r perpendicular into F. So here r perpendicular is equal to this length of the rod. Okay, so students, here this is for one force, and when you have a torque like couple, when you have a couple means two equal and opposite forces along different line of action. So two equal and opposite forces along different line of action make a couple. So what is the torque of the couple? The torque of the couple is perpendicular distance between the forces. So that perpendicular distance is L, and one of the forces, magnitude of one of the forces. Okay, so here the distance between these two forces, here this distance, this perpendicular distance is between, if you are taking this torque, so this torque on this mass at B will be equals to this is your, then you will be counting this distance, means this is the axis of rotation, and this is your point of application of force. So then this will be your r perpendicular. But here in this case, when we have a couple, because we have two forces, they are in equal and opposite direction. Okay, so these two forces. So when we take these two forces, then we don't take it doesn't depend where we are taking axis of rotation, okay, where we are taking origin. So it's simply the perpendicular distance between them, that is the length of the rod, that is L. So here we take L into F. So what is F? G m1 m2 by d square. So that's your F. So F into L. So that's your torque. Okay, that's gravitational torque. And what is the restoring torque? Restoring torque depends on theta. So that is tau theta. So where tau is the restoring couple per unit angle of twist. Okay, so students, it's per unit. This is restoring torque per unit. Okay, so restoring torque per unit of angle. So unit angle over here. So this is for the unit angle. Okay, but what if the angle is theta? So multiply it with the theta. If this is for unit, for 1 unit, okay, so for 1 radian, this is tau. What about if it is theta? Then it is tau into theta. Okay, so this is your so gravitational torque is equals to restoring torque. So this is gravitational torque, gm1, that is F into L. Okay, so it is okay, students. So gravitational torque is equals to restoring torque. Gravitational torque is equals to F into L, and restoring torque is equals to tau into theta. So what is F? G m upon r square into L is equals to tau into theta. So from here we get G is equals to tau theta r square upon L. So we know all these values. We know torque per unit angle of twist, and we know the theta means, I know you have special apparatus. You can find this you know, this distance r is actually what is r here? R is d, right? So write d here instead of r. So we know this distance d. We know this L, that is the distance between these two spheres. We know mn. So and we can calculate the value of G, and this comes out to be 6.67 into 10 to the power 11 Newton meter square kg square. Okay, so just read it out. This is the same thing that I have told you, the gravitational constant. So in the next lecture we will revise acceleration due to gravity of the earth. Students, just be regular. It is very important. Okay, you have nothing to lose but so much to gain. So thank you so much for being